Hello, this is Nicholas. I decided to do a video on Heron's formula for my mu alpha theta students, or for really anyone who is willing to watch, and it's going to be a proof, because I love proofs, of Heron's formula. And if you don't remember, Heron's formula is the one that deals with describing an area of a triangle when you're given all three of its sides, and it relates to the semiperimeter. And the semiperimeter is just half of your perimeter. In other words, if you have a triangle with lengths, side lengths A, B, and C, your semiperimeter is A plus B plus C over 2. And we normally define that to be S for semiperimeter. So, let's start the proof with a triangle. And let's call this side A, that side B, and this side C. I'm going to call the angle opposite to it alpha, the angle opposite to side B beta, and the angle opposite to C, I'm going to call that gamma. And also, if you are kind of confused as to why we always label sides opposite to their angles, it's because in triangles, the length of a side is directly proportional to the angle opposite to that side. In other words, if I have a big alpha, I'm going to have a big A. The bigger your angle, the bigger the side. And you can fool around with triangles to prove that to yourself, but it is a true statement. Now, from the law of cosines on this triangle, I know that c squared is equal to a squared plus b squared minus 2ab cosine gamma. So a squared plus b squared minus c squared over 2ab is equal to cosine gamma. Now, the area of this triangle is 1/2 the base times the altitude, or in other words, the height. Right? It's this segment here is the altitude, or the height, however you want to say it, but just know both of those. And another way for expressing the area of this triangle is equal to 1/2 AB sine gamma. And if that doesn't make sense to you, label this side that I've drawn as H. And now we know from here that if we're considering this right triangle here, we know that sine gamma is H over A, which implies that H is A sine gamma. So normally you'll write the area of a triangle as 1/2 base times height, but what is H? H is A sine gamma, so that's 1/2 A B sine gamma. So, now we know cosine gamma, so we can find sine of gamma, because sine gamma is the square root of 1 minus cosine squared gamma. And normally you'd have a plus or minus here, but since these are all sides with a positive length, we're not really dealing with the negative because lengths are positive. So we'll just consider the plus sign for there. Now, I'm going to kind of write this over here. We get sine gamma is the square root of this. So 1 minus a squared plus b squared minus c squared squared all over 4a squared b squared. And if you don't mind, I'm just going to make this 1 4a squared b squared minus, and then this whole big quantity squared. I'm just going to put it over the same denominator. In other words, I multiplied the 1 by 4a squared b squared over 4a squared b squared. Okay. Let's plug that in. So area is 1/2 AB times the square root of 4a squared b squared minus a squared plus b squared minus c squared squared all over 4a squared b squared. Now realize the square root, well, the square root of 4a squared b squared is 2ab. So this ab and then this square root of a squared b squared are going to cancel out, because when you take the square root, you're going to get ab on the denominator and then ab on the numerator here. So, and then the square root of this 4 will be a 2. So we're going to get 1/4 the square root of, and I'm going to write this 4a squared b squared as 2ab squared minus a squared plus b squared minus c squared squared. And basically, we're going to be doing the difference of squares like 3 times probably on this. So this is a square. This is a square. We're subtracting. We have the difference of squares. So we get 1/4 big square root. So 2ab minus a squared plus b squared minus c squared times 2ab plus a squared plus b squared minus c squared. Little algebra. How do I want to do this? Oh, let's just, I don't want to go too quickly. So 2ab, let's just simplify it some. 2ab minus a squared minus b squared plus c squared, double negative, times 2ab plus a squared plus b squared minus c squared. Okay. Now, okay, realize this here can be rewritten as c squared minus the negative of the quantity a squared minus 2ab plus b squared. Okay, I made the c squared in front and then I just pulled out a negative, so I flip-flopped the signs. And okay, so you're gonna get 1/4 the square root of c squared minus a minus b quantity squared. Oh, it's really raining. Huh. Times, so if you didn't get that, this here, I hope you recognize, is a minus b squared. And you can FOIL out a minus b quantity squared, and you're gonna get this. So I just rewrote it. And now this a squared plus 2ab plus b squared, you should recognize as a plus b quantity squared. So I have a plus b quantity squared minus c squared, and each one of these factors under the square root now are also factorable under the difference of squares. So we get 1/4 the square root of c minus a minus b times c plus a minus b. That's the first factor. Now the second factor, a plus b minus c times a plus b plus c. Now, I'm going to put this 1/4 under the radical. In other words, I know 1/4 is the square root of a 16th. So I'm going to need a new line soon. I'm going to get an even bigger square root. So I'm going to get c minus a plus b. I'm just simplifying the factors for now. C minus a plus b times c plus a minus b. And I'm going to make this over 2. I'm going to make this over 2. And I'm going to have 4 factors. They're each going to be over 2. And 2 times 2 times 2 times 2 is 16. You'll see what I mean here in a second. Times a plus b minus c over 2. Times a plus b plus c over 2. Now, if you remember at the very beginning, I defined S to be a plus b plus c over 2. So this right here is the semiperimeter S. Now, let's subtract c from the semiperimeter. In other words, a plus b plus c over 2 minus c. Now, minus c is really minus 2c over 2. I can make those over one denominator. So in other words, I get a plus b minus c all over 2 is equal to s minus c. So this is s. This is s minus c. This is s minus b. And this is s minus a. So we get the square root of, look at that, s times s minus a times s minus b times s minus c. And that's Heron's formula. That's Heron's formula. That's it. It's a nice formula to use. And a couple things you can actually deduce from Heron's formula are as follows. So realize that from this, no side of a triangle can be greater than the semiperimeter of the triangle. Okay? Because, so let's say, for example, your semiperimeter was 5, so a plus b plus c all over 2 is equal to 5, but then maybe your a was 6. Well, when you do s minus a, you're going to get a negative number, you multiply it all out, you're going to get the square root of a negative number, which is imaginary, and triangles do not have imaginary areas. So, that's one thing that you can kind of deduce from that. So another way of thinking about it is that in any triangle, and this is usually known as the triangle inequality if I remember it right, if you've got any triangle, it doesn't have to be right, just any random triangle, the sum, the sum of two sides must always be greater than the other third side. In other words, a plus b has to be greater than c, if I remember that right. Like, for example, consider this is 3, this is 4, this is 5. 3 plus 4 is 7, which is less than 5, so this is a valid triangle. Now, if we had this side be 8, if we let this side here be 8 instead of 5, we'd actually have an impossible triangle. So we'd still have our 3, we'd still have our 4 approximately, but then we'd have our 8 be going, it's still going. So this right here is not a triangle. It's got this extra part here, so and sometimes I like to ask about that on mu alpha theta tests. Just be aware of that. I guess maybe I should do one example of actually applying this thing real quick. So, let's do that right triangle. Let's do 3, 4, and 5. The semiperimeter of this triangle is 3 plus 4 plus 5 over 2, which is 7 plus 5, 12 over 2 is 6. So the area, and it doesn't really matter what side you let A be, what side you let B be, or what side you let C be, just, be consistent. So our area is equal to the square root of 6, that's S, times 6 minus 3, I guess, times 6 minus 4, times 6 minus 5, and that's all under the square root, so square root of, well, this is 3, this is 2, and that's 1. So 18, 36, oh, that worked out very nicely. 36, which is 6. Oh, that's, see, so the area turned out to be the semiperimeter. It's interesting, right? I wonder if that works for, that's it, I wonder if that works for, that's interesting. I wonder, let's try a 5, 12, 13. Well, okay, area is 1/2 AB sine C. This is a right angle, so I'm going to let this be C because sine of C is 1. 1/2. And the semiperimeter here is 17 plus 13, which is 30, over 2, which is 15. So, and the area by this formula is 1/2. Huh. Oh, well. Oh, that's silly. Wait. Yeah. So, yeah. So if you've got a right triangle, the semiperimeter is the area. Huh. That's cool. That is cool. That's very. So yeah. Huh. I mean, let's see. Yeah. The semiperimeter would have to be the area. This is C, so this is A and B. So the area by this formula is 1/2 5 times 12, which is 30. Wait, 30, 60. Oh, that's not. 60, 30. Okay, let's try Heron's formula and see. I mean, we should get 30. Maybe with right triangles they differ by a common factor. So 15 times 15 minus 5 times 15 minus 12 times 15 minus 13, which is that's 10, that's 3, that's 2, so 60 times 15, well, 60 times 10 is 600, add another 300, we get 900, square root of 900 is 30. So maybe in right triangles they differ by a common factor, and I guess just here our common factor was 1. I believe that's all I have for now. I am in a separate video going to do proof for the law of sines and cosines, because I just wouldn't feel right teaching you it if you guys hadn't known the proofs for it. So I believe that is all for now, and we're done.